Good afternoon, my name is Dillon, and I'm working with connections to beginning circuit boards for CERN. My mentor is Aditya Delakoti, and we work in Professor Forrest Brewer's lab, which is funded through High Granularity Calorimeter Studies, or HGCal. Now, one of the hottest places in the known universe is actually much closer than some of you may think. No, it is not the sun, which is only at 15 million Kelvin. That's not very hot. I mean, come on. Something much hotter that is actually even closer than the sun is a lab in Europe, in Geneva, Switzerland. The CERN lab is one of the leading researchers in physics, and they've seen temperatures up to 5.5 trillion Kelvin. Now, they do this using their Large Hadron Collider, which is 17 miles in circumference, and it takes particles and it speeds them up to the near speed of light until it smashes them together, which is this intense collision which releases an intense amount of energy, which is one of the reasons why it's one of the hottest places in the known universe. Now, these collisions don't just release energy, they recreate the Big Bang in a sort of way. Right after the Big Bang, the universe is superheated to where the building blocks of matter were actually in this primordial soup. And ever since I started science, I was like, okay, yeah, I first learned that atoms were the basic building blocks of matter. But then later on, I found out there's protons and neutrons which make up atoms. But then if you go even later on, you find out that there are things called quarks and gluons, which even make up protons and neutrons. Now, this soup of quarks, protons and gluons is basically how the universe began. And this is a great study in CERN. They want to figure out better ways to detect what the soup does, different particles, and different kinds of radiation that go on after these particles have collided. Now, all this kind of unknown stuff seems kind of daunting, but they've started to make great leaps in detecting what goes on in different interactions, and so far they've done this with a high grid of silicon detectors. But then the next step is to actually make connections from the detectors to computers to crunch the data. And this is the main focus of the lab I'm working in, is to work on these connections. So first off, they need to withstand a large amount of radiation, because as you can imagine, as particles collide, these high temperatures, different reactions going on, there's a large amount of radiation that can corrupt the data, so these connections need to be able to withstand a large amount of radiation. However, they also need to have very high data rates, because right now we're just seeing little blips of data in the overall possibilities of what we could be learning about these interactions. So the faster the data rates, the more data we can extract. A very viable option for these connections are circuit boards. Circuit boards are present in almost all modern electronics, whether it's your electric toothbrush to your computer to your new Tesla. They all have different sorts of circuit board applications. Now, this was the main focus of my research this summer, is learning how to make circuit boards and different applications for it. One of the reasons why this is a viable option is because it overcomes two of the main constraints associated with CERN, which is space and power. Because CERN is so high-tech, there are millions upon millions of different moving parts that are independent of each other, so space is very constrained. So having things as small as possible is the best solution, which is why circuit boards work well, because you can have them very flat and make them very small. Another reason is power. Because space is so constrained, it's very difficult to get power into kind of the heart of the reaction, and then make sure to power whatever connection you have taking it out. So the first overall goal I have after learning how to make circuit boards is to test integrated circuits. And you can see these integrated circuits here are these little black chips on the circuit board. And these new chips are being developed by the lab I'm working in. And after I finish making the circuit board, then they will use their chips to test to make sure that they're working properly. Now, the next overall goal I have is to make a long printed circuit board. Now, oh cool, just send it into fabrication. It's not quite that simple, because they want it to be roughly 1 meter to 1.5 meters long, which is unorthodox for this. The one I'm actually working with is only 3 inches. So 1.5 meters long circuit board is unorthodox, which instead what they're going to do is to do a grid or a ladder of different smaller circuit boards to serve as a larger one. There are some problems associated with this, because whenever you send data down a transmission line, this is regardless of a circuit board just sending data or a signal down a transmission line, you will lose some of your signal, as you can see in this graph. So this is just a simple experiment previously done at the Brewer lab, where if you send this signal down, represented by this blue line, The signal you receive on the other end is represented by this green line. So it's quite obvious you definitely lose some of your signal, which you do not want in a very high precision environment like CERN. There is another problem associated with this. Due to imperfections in connections, you can actually have reflections as well. So not only do you naturally lose data just by the connections, you could actually have some of the data you get through to be reflected back. As you can see by this graph, is the blue is the signal that was sent down, and the red is the signal that was received. So some of the data was reflected back towards, which again causes overall loss of data, and then you have less data to work with and crunch and detect what goes on in the reaction. Now, the actual circuit board I designed, which again was the main focus of my goal this summer, is a pretty simple 4-layer circuit board. The top layer is the component layer, which is where you would put different connections. You could have different routes. Just that's the top of the board, that's what you see. The next is a ground layer. It's just solid copper because you want to have a solid connection beneath anywhere you're routing. Again, we have another signal layer, which we can put traces to send signal down, and then finally another ground layer. So this is typically what the circuit board looks like in the software I'm using called Mentor Pads. So right here, these are each a connection, and this outline is just the board itself. Now, this is what the connection looks like. It's 12.5 millimeters, fairly small, and it has 100. Each of these is a pin, which is where it's copper, so it can take a signal and conduct electricity to send it on. Now, you can not just have components on this component layer, you can also have connections, which is a copper root. So in this ladder, we have some signal sent down, it hits the connection, then it hits the root, travels along the circuit board, hits the next connection, and then goes on. Now, you can also, what if we wanted to have signal sent through the signal layer? You can't connect to the middle of the board, so you have something called a via. So a via is a hole between layers that you can then connect from the top, goes down, and then out the other side. You can also have through holes or mounting holes, which is where you can put screws to secure the board on, or to secure whatever device, in this case we have a connection, onto the circuit board. So this is what an unrated board looks like. Again, this is what the connection looks like, and this is just, each of these are called footprints, which is you have to design kind of where each thing will go. In this simple model of circuit board, we just have a connection footprint on each end of the board. Now, this is the board after it's started to be completed. So these black squiggly lines here are the roots, and you may be wondering, why are they wavy? Why aren't they just straight across? Like, Dillon, this is not the most simple. This isn't the simplest way you could have done it. It's like, yes, it's true, but each of these roots needs to be the exact same length, which can prove quite tedious, to be honest. Making sure each of them are the same length, because you don't want to have different length roots, because then you have different signals getting there at different times, and you want everything to be simultaneous. So this is the top layer, component layer, where we have the connections and then the roots together. But something you also may have noticed is why does it just go from the pin just over a little bit? These are the vias, because we have 8 of the roots on the top component layer, and then we have 8 of the roots on the signal layer. So first component, next we have the ground layer. So this is a solid copper, and again, these white holes are the mounting holes. It just goes straight through the board. And then these black holes with the white outline are the vias. So because the vias can conduct electricity, they are black because they're plated with copper. So again, as it goes through the via, then we get to the third signal layer, where again we have kind of, it's called, the squiggles are called tunes, to make sure that every length is the same for the root. To make sure that they all get there at the same time. And then finally, the bottom of the board is again solid copper with 8 mounting holes. Now, this is what the finished board looked like. I just finished this on Friday and sent it in for some preliminary testing, and so far it's looking good. But this summer's mainly just been about learning how to learn about how to make circuit boards and physically making it and checking it. So experiments that I want to do, I haven't been able to do yet, but since I've started to get this done after further checks and making the other board, I'll get to do those. And these tests include testing the integrated circuit. So where, after I design each of these boards, we'll put an integrated circuit on the board made by the lab, and then just make sure that they're kind of talking to each other correctly, because they're form a connection. So all we really care about is to make sure the information that gets sent to the connection is the same that the information gets sent out. So to do that, we simulate data that we would assume would be similar to what the detector would pick up. So we use this using a laptop and a data controller. And then again, we just want to make sure that that data is the same as the data that we get out. So this really isn't, this is just to simulate the data and to make sure we're doing everything correctly. But this is the main focus, making sure that the information going in is the same as the information coming out. Now, the next experiment that I would like to do is using the long printed circuit boards. So we have a similar setup where we have the signal generated most likely by a laptop and FPGA, and then we attach that to with a 3-inch circuit board that I just finished, and that is going to be 0.0762 meters. And because it's that length and we want it to be 1.5 meters long in total distance, that's going to be roughly 20 circuit boards. And there are some people that say that there's going to be too many reflections because of imperfections in the connections after about 3 or 4 circuit boards. So we may have to adjust the size of the smaller circuit boards so that we would only use 3 or 4 instead of 20. But then after, we can add the connection, which again looks like this, and then we would have the ladder, which would then send the signal from here through all the boards and the connections down to the signal and make sure that there's the same. Now the point of this experiment is to see at what frequency the ladder can actually function well, because at higher frequencies it's more likely to get more reflection or more data loss. So we want to hopefully get around 5 gigahertz because that's where the experiment wants to be run, and we can have the best possible output. Now, I'd just like to thank Professor Forrest Brewer for allowing me to work in this lab. The Brewer Lab total, Merit and Prashantha have both been a great help to me. EUREKA and CSAP running great programs, really helping a lot of undergrads learn more about research. And finally, my mentor Aditya, who came today. You've been a great help. I thank you again. Thanks. Any questions? Yeah.
Seems like one of your, or two of your largest problems is having a large amount of the signal go through and also the reflection, which reminds me of one of the photonics presentations previously. So have you ever thought about using photonics to minimize reflection?
Personally, no. I don't know a lot about photonics. I'm just learning on circuit boards. So that's possibly an option. I'm not sure if that would still work in the same environment just due to different constraints, but that is an option to look into. Yeah?
Do you also have to deal with that noise from the chips that you put on there?
I haven't gotten to actually put the chips on there, but that's probably going to be an issue too. The main issues are something called impedance, which is calculated through how wide the roots are, how thick your substrate is, what the dielectric constant is, which just means how well does it conduct electricity. And there's just a lot of different factors that go into making students pass up, but noise is also probably going to be an issue. Yeah.
So you said a 1 meter long one is unorthodox, but why is it not possible?
So to make one that big, most companies just won't fabricate it because there really isn't a whole lot of need for one that large. Talking with some people in my lab, there are printed circuit board light things that can be that big, but instead this is coming from the people at CERN wanting to say, hey, try to make a ladder and see if that works, and if so, great. If not, we'll try to find another option. But yeah, not as much. Yeah.
So why do they want the board to be that light?
I'm not sure why they want it to be 1.5 meters long, just from the constraints. Just because if they can get it out, the farther they get out, the more space they'll have. And because circuit boards can provide so many different leads, if they get it out 1.5 meters, they have a lot of leads to then use wires to connect the data out. But why exactly 1.5 meters long, I'm not sure. It's also rough. They said 1 meter to 1.5 meters. So it's just kind of an estimate of why they want it long. But I can talk to my mentor and we can meet after if you want to find out exactly.
Okay, thank you.
Thanks.